Dear student, colleagues, and on the viewers who are watching this program live on Facebook page Physics Adda and Facebook page Energy of the Future Information Center on Nuclear Energy Dhaka. And I would like to welcome you all to our webinar. A good evening to all here in Bangladesh and good afternoon to all those who are watching this program live from Russia. Hope you are well and safe from corona pandemic. Today, I'd like to welcome you all to a joint session between Pabna University of Science and Technology, Pabna, Bangladesh, and National Research Nuclear University, MEFI, Moscow, Russia, on a webinar in nuclear reactor physics and nuclear reactor power. And I'd like to say thanks to Energy of the Future and the Information Center of Nuclear Energy Dhaka for helping us in arranging this program. So today we have with us Dr. Alexander V. Nakhabov, Associate Professor, Department of Nuclear Physics and Engineering, MEFI, Moscow, Russia, joining us from Moscow, Russia through SteamYard. So, and he have already joined with us, so I'd like to welcome our speaker. So good afternoon, sir, and good evening here in Bangladesh. So I'd like to say thanks for accepting our proposal to deliver your speech in our webinar. And I'd like to welcome to our university and Bangladesh through SteamYard. Though you have already visited Bangladesh this February, maybe.
Yeah.
And I think this webinar is going to be your first collaborating program with any university of Bangladeshi university, isn't it, sir? Or you have already collaborated with other university with the webinar?
Do you mean universities from Bangladesh, our partner universities?
Yeah.
Yes, you know, maybe. Of course, first of all, now we have some memorandum of understanding, first of all, with capital, with Dhaka University, with Bangladesh University of Engineering and Technology. But especially after Olympiad in this February, I feel we are very interested to start collaboration with local universities like your university, Pablo. Because I know your university, I know university in Rajshahi. Moreover, some students in MEFI University in master programs actually graduated from local universities. So of course it's another good direction of our collaboration with universities in Bangladesh.
Okay. So for this reason, actually, as you accepted our proposal, I'd like to say thanks again on the behalf of the Department of Physics, Pabna University of Science and Technology. Actually, Dr. Alexander, actually, he's a very good nuclear scientist and well-known nuclear scientist in Russia and one of the best nuclear scientists in the world. And actually, he believed that nuclear technology is a very important part of the science and industry. And it is very important for agriculture and medicine. And as we are living in a corona pandemic situation and all the institutions have been shut down due to corona pandemic since March 2020. So it's very difficult for us actually to continue our normal program, you know. And for this reason, we have started some online program like online classes, online seminar and webinar. And I actually happy to share that in those webinars, actually the physicists from different countries are coming as a main speaker. And actually by this way, actually, the student actually benefited because they can interact with the famous scientists from online and they can ask their question. And this is our small attempt. And the aim of this webinar is to encourage our students. And we have chosen today's webinar topic about our nuclear reactor physics and nuclear power plant because you know that we have already started our first nuclear power plant project and Bangladesh government have already started. And hopefully we'll start or nuclear power plant will start its operation within 2023 or 2024. And for this reason, actually, we need a lot of skilled manpower. Actually, and the aim of this webinar is to encourage our next generation and our students mainly to feel interest in this field. So actually, we in Pabna actually is very closest to our nuclear power plant, and we feel that we have a lot of responsibility in this regard. So I hope this webinar will help a lot of our students and who can directly interact with our speaker, Dr. Alexander sir, and they can directly interact with him and ask to him about this lecture. And for those who are new, and I'd like to share that we have divided our webinar in 3 parts. First, I'd like to introduce our speaker with you, and then there is a time where our speaker will deliver his speech. In the last part, we have a discussion session. In that session, actually, anybody can join with us, and there is another option. Anybody can ask question by commenting in the Facebook. So before going to our speaker, I'd like to say something about our speaker. So you have already came to know that today's title of our today's webinar is the nuclear reactor physics and nuclear power plant technology and safety. And our today's speaker is Dr. Alexander V. Nakhabov. He is working as an associate professor at the Department of Nuclear Physics and Engineering, Obelisk Institute of Nuclear Power Engineering, National Research Nuclear University, NNP, Moscow, Russia. He is interested in the development and application of methods and automated system for non-destructive testing and technical diagnostic at the nuclear power plant, especially regarding methods and algorithms for data processing and analysis. So, as we have already came to know that he's one of the best nuclear scientists in Russia, and in the group of Russian specialists, he participated in service welding joint inspection for equipment and pipeline of Pionan nuclear power plant project, Unit 1 and 2, China. And he's involving in managing of several bachelor, masters, and specialist programs, as well as in education for foreign students in nuclear area. Among his courses are control theory basics, non-destructive testing on nuclear power plants, introduction in nuclear power engineering, nuclear technology and monitoring, control and diagnostics system in nuclear power plant. As a lecturer with Rosatom State Cooperation, he provided many open lectures all around the world regarding different aspects of nuclear engineering and nuclear technologies. And this is one of the pictures where he's delivering his speech in front of a television channel, and where he's actually believed that nuclear, which I have already told that he believed that nuclear technology is very important. So his course in MEFI, Introduction in Nuclear Power Engineering, Monitoring, Control and Diagnostic System in Nuclear Power Plant, non-destructive testing method and destructive testing method on nuclear power plant and nuclear technology. And we came to know that he has several publications in different journals worldwide. And thanks for your patience. And now this is the time for going to our speaker. So I'd like to welcome you again, sir. So it's your time. You can start your session, sir.
Okay, thank you very much. First of all, now I'll try to make full screen my presentation. Is it okay for you?
Yeah, it's okay, sir. You can.
Okay, great. So thank you very much, Dr. Pretam, for your introduction of me. Yes, I visited Bangladesh in first time in this February and visited not only Dhaka, but especially region of nuclear power plant under construction, Ishwardi and different areas around. So, of course, now it's my pleasure to provide this presentation for students and faculty members of Pabna University, first of all, of Science and Technology. And, of course, you see on this slide this topic, nuclear reactor physics and nuclear power technology and safety aspects. Of course, it's just impossible to put all information regarding all these areas in one short presentation. And when I discussed with Bangladesh colleagues and Russian colleagues about most important accent of today's presentation, of course, I think, first of all, I'd like to say about importance of studying in physics and in different areas of Physics and Technology Engineering for nuclear power plant. So first of all, my goal is to involve young future specialists from Pabna University, maybe from other universities in Bangladesh, in this very interesting and very important area of industry for your country. So, first of all, of course, you know, now we are talking about this topic, of course, first of all, because, you know, your country now is so-called a newcomer country, like IAEA said. Newcomer means Bangladesh now is country just to construct first nuclear power plant in your country. Rooppur nuclear power plant, located nearby of Pabna. And on this slide, you see project view. As I know, especially for your country, Pabna, for your country, it means Rooppur nuclear power plant. 2 power units of VVER 1200 megawatts. And this photo in, I hope you see my pointer. Yes, Dr. Pretam? Do you see my mouse pointer on the screen? I hope so. Okay, so you see this picture of your site nowadays, from site of Rosatom. So nowadays this nuclear power plant is under construction, but training of specialists, of course, already started several years ago in Russian Federation, and retraining of specialists in Bangladesh, because we should to have some part of personnel before startup of power plant in your country. So, first of all, of course, I'd like to very briefly explain idea. I hope many of my audience maybe know about this. But first of all, of course, I'd like to make some essence about this. So, as I know, especially for Bangladesh, nowadays the main source of energy, of course, it's not nuclear right now. It's first of all traditional power engineering. Traditional power, it means thermal power plants. First of all, using coal and gas. And idea is simple. Technical idea how to produce electricity from thermal power plant. We'd like to use electric generators to produce electricity. And only one question is how to rotate this generator with very high frequency. At least approximately like frequency in your supply grid. 50 hertz, for example. On majority of thermal power plants, usual steam turbines are used for this purpose. So we can use turbine connected on the one shaft with a generator, and we should to provide a lot of steam to rotate this turbine. So the next question, of course, what is source of this steam? For usual thermal power plant, we use boiler and use, for example, coal, like on this slide. We use coal as fuel just to burn in this boiler or furnace. And we have secondary circuit in this sense. We have some circuit with water. And of course, while going through this boiler, of course, this water gets hot. And finally, this water transforms in steam. And this steam will rotate turbine, and turbine will rotate generator as well to produce electricity. After this cycle, after rotation of turbine, this steam is needed to be condensed again in water because we want to close this cycle. So in special turbine condensers, this steam will be condensed and will be used again and again in this cycle, many times. And we should to use some outside source of, first of all, water as usual, like river, ocean, maybe lake, like a source of cooling water for condensers. So that's all. That's all idea, and all pollutants, all different elements from thermal power plant, first of all, originated from this burning of coal. So this idea. When we say about nuclear power plant, on this slide you see very prominent picture about PWR reactor principle of operation. Actually, all part to the right from this reactor building, turbine, generator, condenser, feed water pump, actually all this part is very similar to the same part from thermal power plant. Actually, the difference is in this part. In this part, when we say about how to produce steam, if in usual thermal power plant, the boiler was used for this purpose, in nuclear power plant, actually we use energy from nuclear fuel. So we should to have nuclear fuel in some part of this reactor installation. Then we can initialize a fission reaction of uranium, and this fuel will get hot, and using water as coolant of primary circuit, this heat can be transferred from fuel to water, first of all, and then in special equipment called steam generator, this heat can be transferred from the primary circuit to the secondary one. And finally, in secondary circuit, the steam can be produced, and the steam will be rotate turbine, and the same cycle like for thermal power plant. So actually, all main equipment of nuclear power plant and all main difference maybe from thermal power plant actually is concentrated inside of this reactor building containment. So this is my idea. And of course, as I said in the start of our presentation, first question, I guess a lot of students in today's audience is students from different specialties, different programs, maybe bachelor's, maybe master's. And of course, first question can be, where is physics needed at nuclear power plant? Because nuclear power plant, it's a huge enterprise, huge industrial enterprise to produce electricity in safe manner and so on. But this question is very good because moreover, in Russian Federation, I guess in many Western countries, many years ago, when we just started to develop this area, actually faculties of physics was the first like cradle of future specialists in this area, because physics actually basic course, basic major for nuclear power plant. So on this slide, actually you see not all, but majority of main shops or divisions of nuclear power plants and departments divided in 4 big areas. Actually, in structure of Russian design nuclear power plant, VVER, actually all 4 areas, operation, repair, safety, and automated process control systems, actually all 4 areas correspond to deputies of chief engineer. On nuclear power plant, there is chief engineer of nuclear power plant, and there are deputy chief engineer in operation, repair, and so on. So you see, first of all, the main part, operation, we say about reactor shop, turbine shop, and chemistry. Chemistry shop, actually, it's special division on nuclear power plant intended to provide all operations for water treatment, filtering, preparation of this water for operation in nuclear power plant, and so on. Special department. The next area, safety, very important ones, because operation with divisions, first of all, intended for main technological process to generate electricity on nuclear power plant. But when we say about safety, all these departments, first of all, are designed to provide safe operation. So you see the main departments: nuclear safety and reliability, radiation safety. This abbreviation stands for spent nuclear fuel storage facility, and special shop of processing of radioactive waste generated during operation. Next area, repair, centralized repair shop, material science lab, and non-destructive testing or inspection department. All these divisions and departments to provide maintenance and repair during all life cycle of nuclear power plant. And finally, automated process control system, or in many sources you can find instrumentation and control system. It's electric shop, instrumentation shop, and diagnostics department. Actually, for personnel in all these departments, as I know, it's must have to have in curriculum, in bachelor's or master's program, the main physical courses as some foundation or some base for future knowledge. The next question, okay, physics is very important as science and very important for future personnel of nuclear power plant. But the next question is which physics areas are most needed for personnel of nuclear power plant. Actually, I'd like to comment this idea on this slide because physics, as I said, actually like foundation of all future knowledge in this area. Of course, this picture, first of all, corresponds to Russian tradition, Russian practice in training personnel for nuclear objects. First of all, as usual, we say about general physics. General physics, I think in Bangladesh, it looks like this way, because in our universities, in MEFI University, after enrollment in university, for example, on bachelor program, students during first 2 years will have courses in general physics, first of all. So general physics, the main areas, mechanics, molecular physics, electricity, magnetism, waves, and optics. And as usual, for all nuclear-related specialties, during first, not 2 years, actually 1.5, 3 semesters. During all 3 semesters, this foundation, these base courses in physics will be provided. The next step is more specific courses, first of all in atomic physics and then in nuclear physics. So during second and third years of education, students will get these courses, atomic and nuclear physics. And actually next layers, theoretical physics, you see selected areas, and quantum mechanics and statistical physics. These courses, it's not for all specialties. First of all, for some selected areas, for some selected majors, students can get additional knowledge in deep knowledge in physics from theoretical and moreover from quantum. But when we say about Bangladesh situation, of course, first of all, we should to keep in our minds what we say about, first of all, about preparation of personnel for nuclear power plant. It means for all areas around operation, nuclear power plant. Of course, in Russian Federation, we say about not only operation, we say as well about design, about development, about research. In Bangladesh, as I know, nowadays there are special facilities. There is nuclear research reactor to provide research in this area. Of course, when we say about research, of course, we should to say about more deep courses in physics, like I said, about theoretical physics, quantum, and so on. But for operation, of course, quantum mechanics, maybe it's so deep knowledge. It's not needed for usual operator. But for researcher, yes, it's maybe very, very needed and interesting. And in other part of my presentation, I'd like to describe different areas of knowledge regarding for nuclear power plants and to provide information about courses, about specific courses in curriculum of nuclear programs. In our, of course, I used MEFI University like example in this case, just to give you some understanding of how to provide learning process in this area for students and for foreign students as well from Bangladesh. And I think it will be very interesting for you because all students from physical faculties nowadays, if the students will choose this path, this way of studying in nuclear specific areas, just for your understanding of this area. Of course, let's start from the heart maybe of nuclear power plant. Of course, the main important thing, actually, it's nuclear fission chain reaction. I hope maybe you know this kernel idea for all nuclear power plant operation. So first of all, we say about nuclear fission reaction. Fission reaction, when single neutron will collide with nucleus of uranium-5, uranium-235, and in this case we will get two byproducts. Two byproducts, as usual, in more with more probability, it's kryptonium and barium, and we have several neutrons after these reactions. And idea is simple. If we can organize our fuel in such a way for all these neutrons, if we find new nucleus of uranium-5, in this case we can get chain reaction. In reactors, in power reactors like VVER, our idea to realize this reaction in controllable manner, because you know, nuclear can be not only civil, but there are military applications. Of course, when we say about nuclear power plants, we say only about civil applications, and we say about safe and stable production of electricity during many, many hours, months, and years. And in this case, of course, we should to control this reaction in suitable manner. And of course, complexity of task, of calculation, and so on. Because in a real nuclear reactor, the structure is not simple. Because on these pictures, on these photos, you see in the right corner, it's actually a big photo with multiplication, a big photo of one of parts of fuel assembly. Because in left corner, you see totally one fuel assembly of VVER 1200 reactor. So fuel assembly actually like a brick, like unit of core of reactor. And in VVER 1200 core of nuclear power plant, there are many, many dozens of these fuel assemblies, more than 180. So all nuclear fuel actually is organized in this form. So on this picture, we can see a lot of rods, actually it's fuel rods. Fuel rods, in one fuel assembly, there are more than 300 fuel rods containing uranium. Actually, you see very thin and very long tubes with all uranium pellets inside. And all fuel rods are hermetically sealed by special welded. So a lot of fuel organized in this hexagonal form. And you see some guide tubes and so on. So this is construction of fuel. And using these fuel assemblies like initial elements, like some primal units, we can actually construct, we can organize all reactor core. So on this picture you see actually all reactor core of VVER 1000 reactor, 1200 megawatts. But actually this course looks similar. And in dark regions you see some core baffle and core barrel around. So if this is nuclear reactor core, heart of this reactor, and fission reaction of uranium fission will be realized inside of this core. Of course, before operation, during development of construction of nuclear power plant, of course we need to calculate. We need to calculate optimal from optimal distances and so on for all this construction. And as I said, and as I say a little bit later, it's very important during operation too. So, of course, first of all, when we say about deep education in nuclear, we say about courses, so-called neutronics. Neutronic courses. On this slide, you see maybe the main four courses: nuclear reactor physics, kinetics of nuclear reactor, dynamics, and neutron transport theory. Actually, I guess, except of neutron transfer theory, it's a separate course in many universities. All others, kinetics and dynamics, can be considered like sections of nuclear reactor physics, because in different curriculums it can be different courses, or all these courses can be consolidated as one, as nuclear reactor physics, for example. So all these courses about how to investigate, how to calculate fission reaction, paths of neutrons inside of materia, different possible variants of interaction of neutrons with fuel, with different materials, and so on. Because if you look again on core, you see, of course, it's a lot of uranium inside, but a lot of different materials, like material of fuel rod cladding. It's special zirconium alloy and steel. A lot of steel constructions inside. Inside of every fuel assembly, not every, but majority of fuel assemblies, there are control rods. Actually, in VVER reactor, control rods not separated from fuel assemblies, but actually in many fuel assemblies, special clusters, so-called clusters of control system, located in these tubes. So in this way, we can distribute these control rods inside of core, just to provide more even, more well-distributed thermal production inside of reactor core. So, of course, we should to provide special courses, first of all, regarding specific nuclear knowledge. And you see all these courses on this slide. Of course, first of all, these courses is needed for specialists of reactor shop and specialists of Department of Safety and reactor diagnostics. When we provide these courses, of course, first of all, it's lectures, it's seminars with solving of different problems and so on. If you say about using of computers, of information technologies, first of all, of course, it's codes, special programs, codes to calculate neutron flux, neutron interactions, and so on. And of course, all these codes, it's about computers. This knowledge can be provided in special display classes and so on. But learning of these Neutronics courses, it's very desirable to have some labs. But to provide labs, it's hard enough, because we need to have special facilities as usual. In our university, we solve this problem by collaborating with our partners in Russian Federation, in Obninsk, because I hope you know, Obninsk it's cradle, it's a place of birth of civil nuclear engineering in the world, because the first in the world nuclear power plant was put into operation in Obninsk especially. So on this photo, actually, you see, like example, only one of possible variants. On this picture, it's actually so-called fast neutrons facility, fast neutron stand testing facility, located in Institute of Power Engineering in Obninsk. And actually, this institute, it's research institute. It's actually institute where first nuclear power plant in the world is located. So our students during education, during 4 years of bachelor program, have a possibility to have a labs on special equipment in our partners organizations. The next level of consideration, maybe, if you would like to see all equipment together. On this slide, you see reactor installation. It's so-called primary circuit of VVER 1200 installation. So you see reactor vessel in the center, 4 steam generators, and as well 4 main circulation pumps. 4th pump, I guess, should be besides of this construction. And we have special equipment called pressurizer, this very big one. In the reactor installation, there is only one pressurizer to provide actually pressure inside of circuit. And you see actually elements of safety system. It's a hydroaccumulators of emergency core cooling system. In VVER 1200, there are 4 hydroaccumulators of first stage. So it's so-called reactor installation with 4 loops of cooling. And of course, when we say about working principle of reactor, first of all, we should to say, okay, first element, it's fission itself, like we just discussed, fission and heating of fuel. But next, we should to consider how to get this heat from the fuel and how to transfer this energy, finally, from nuclear fuel and up to turbine. Actually, in nuclear reactor, we have several transfer of energy from one kind to another one. So, of course, first of all, we say about coolant and about water, because VVER reactor, in this reactor, water is used like coolant of primary circuit, and water is used like working agent of secondary circuit. Anyway, water plays very important role in this reactor. And on this slide, you see, for your understanding, cross-section of reactor vessel of VVER. And during operation, water will go in this bottom line of nozzles of primary circuit. And we have a core barrel. Core barrel, it's special construction, which help us to organize this flow of coolant. So water will go inside of reactor through this intake, go down in a small gap between core barrel and wall of reactor vessel, and through special holes inside of this core barrel, this water go inside of core, go through all fuel assemblies, and in this area, heat from nuclear fuel just transferred to water, and then through upper line of nozzles with hot water go out through reactor vessel. So this idea how to organize cooling process. And you know, it's impossible to get photos of working reactor, because during operation reactor vessel, of course, is closed, is tightly closed with special construction. And but of course, there are several options how to see, how to look at nuclear reactor vessel. First of all, of course, you can see this reactor vessel during manufacturing on manufacturing plant. And then after mounting on nuclear power plant, on this picture, you see actually special stage of pre-setup procedure called reactor flushing. And actually, this is reactor vessel without lid. And this is shaft, without a concrete shaft of reactor. This photo is made on Novovoronezh nuclear power plant in Russia, as I know, the same type of VVER 1200. And you see from inside nozzles of primary circuits. And actually, this nozzle of, I guess, this nozzle of maybe emergency cooling system, or from pressurizer, yes, special connecting line between pressurizer and reactor vessel. And fresh water just flush all pipelines during this stage of testing. So it's just very interesting photo to give you some understanding how it looks like. The next very important element when we say about thermal hydraulic processes inside of reactor and about operating, it's steam generators. Steam generators actually equipment, it's actually bridge between primary circuit and secondary one, because we should to have special equipment to realize this process of transferring heat from primary circuit to secondary circuit. And actually this process is organized inside of steam generators. Idea is to provide a lot of very thin tubes. A lot of means, you see, more than 11,000 of heat exchange tubes. very thin, only 1.5 millimeters in diameter. So a lot of tubes in special manner organized inside of this steam generator. And there are two collectors you see on this slide. In one collector, hot water from reactor go inside of this steam generator and will distribute through these tubes. And then this water just go through these tubes and collect in the outside, not outside, but intake and outtake maybe collectors. And then this water will go again to main circulation pump and in the reactor as well. But during this way through steam generator, all these tubes just immerse inside of water of secondary circuit. So water of secondary circuit just filled this steam generator, not fully, just to close these tubes, heat exchange tubes. So of course, hot water of primary circuit will boil water of secondary circuit, because pressures in primary circuit and secondary circuit, of course, very different. Pressure in primary circuit of VVER 1200 is approximately 16 megapascals, and in secondary circuit only half of this number, only approximately 7. You see 7.84 megapascals. Of course, water of secondary circuit start to boil, and we get steam. We get steam, and the steam is collected through these pipelines in the upper part in special collector, steam collector, and then all the steam can be provided for turbine. So of course, these steam generators are very important equipment. Of course, first of all, due to complicated structure, complicated design, because we'd like to maximize surface area of all these tubes to improve heat transfer. But of course, it's very hard to provide integrity of these tubes during operation, because we have huge gradients of pressure and temperature alongside tubes wall. So it's very important element. And on this picture, you see actually steam generators. Steam generator, it's not cross-section, it's actually a real photo from manufacturing plant. On manufacturing plant, all these tubes, and you see all these heat exchange tubes. Finally, of course, all this part will just be closed by one of sides, actually like lid of steam generator, and this connection will be welded. But during manufacture, you can see tubes and special steam separated construction in upper part, and black, like dark elements, actually connectors, no, not connectors, but collectors of steam generator. So very big, very important equipment. And of course, first of all, when we say about main scientific areas, main courses, we say about thermal hydraulics courses in this area, because to work with this equipment, you should to have knowledge in fluid mechanics, first of all, in heat and mass transfer, and metrology. Metrology, actually, I guess you have this course in your university. And metrology, of course, first of all, it's course about how to provide measurements of different parameters and so on. But for example, in our university, we have very long practice to provide course of metrology based on special equipment. First of all, for labs, first of all, thermohydraulics equipment. Because on nuclear power plant, of course, we say about measurements. But many measurements, first of all, it's measurements of flows, flow rates, measurements of pressures in different pipelines and so on. Of course, there are measurements of temperature, of liquids, of steam, and measurements of temperature of some elements. So metrology can be based actually on equipment used for thermohydraulics. And when we say about education in this area, of course, as well, lectures, practices, and it's very important, laboratory works, laboratory practices. In our university, we have special resource center, because in MEFI University, actually nowadays there are 3 resource centers, 2 centers located in different cities in Russia, many kilometers away from Moscow, and 1 center actually is located in Obninsk branch of our university. And you see on this and next slides several very interesting facilities. Not all, but some selected. First of all, on this slide, you see special test installation research reactor. It's actually like model, like a small model, because a real research reactor, as I know, has several meters, at least, reactor itself. Of course, we have some model, approximately 1 meter in height, and approximately maybe 1 meter in diameter. So, like model of reactor and pipelines around. And of course, we have some instrumentation to measure flow rates, pressure, and so on. This installation was used for many PhD physicists, for diplomas of students, and so on. The next equipment, circulation loop. Model of circulation loop. Again, big tank is considered like a model of reactor vessel, and very long tubes are used just to model different models of flow of water, first of all. And you see, we can model different angles because actually you can use just simple like construction. You see, you can insert any different form of tubes, of pipes between, just to investigate flows of water, or maybe I don't know, maybe you can model steam, just to research in thermohydraulics. This installation is intended to make research of channels of different forms. First of all, first channel is circular, of different diameters. The third one is with square cross-section, and the last with triangular cross-section. So we can just insert channels of different geometry in this installation and provide different research of processes in these channels. On this slide, you see special test installation to make research in two-phase flow. And this tube is transparent. Transparent because we can use different color agent. And it's very interesting to model situation with separation of flow between, for example, gas and liquid. And we can visualize front of or boundary, or can visualize some layers inside of flow. So a special installation to provide such kind of research. And special installation to model hydraulic hammer. I hope you know it's a very interesting but very dangerous effect in hydraulic systems, because and especially on nuclear power plants as well. It's special kind of phenomenon. And this installation, first of all, designed to provide research for students and for master's PhD in this area. So we can model this effect in safe manner and to investigate actually this phenomenon. All these slides was about thermohydraulics and heat and mass transfer courses. When I said about different shops and divisions on nuclear power plant, I said about chemical shop. Of course, as I said, on this picture, actually you see during mounting works before operation. This is this chemical shop on nuclear power plant in Russia, VVER 1200 megawatts. So you see different elements, maybe it looks like filters. You see special motors and pumps. And of course, when we say about chemical shop, of course, first of all, it's chemistry. But it's actually not chemistry, but it's mix. of physical and chemical processes. And of course, in our university, we have special courses, not so many, actually. For operating personnel, it's only one course in physical and chemical processes in nuclear power plant. It's course designed especially for students for this shop. Next level of consideration of nuclear power plant, it's actually secondary circuit, because now we just considered core of reactor and equipment of primary circuit. So actually equipment of primary circuit is reactor vessel and all internals. It's steam generators, main circulation pumps, and pressurizer. So with all of this, it's main equipment of primary circuit of nuclear power plant. But of course, we should think about secondary circuit. From one side, as I said, a secondary circuit of nuclear power plant is not so specific for nuclear, because actually it's the same area like for thermal power plant. Of course, yes, turbine for nuclear power plant has our construction, has some specific in details, but idea is the same. But nevertheless, secondary circuit, of course, is very important, because especially in this circuit, we can provide transfer of energy from steam to turbine, and finally to generator. So on these pictures you see, first of all, turbine. On this picture, this turbine with no covers installed. Of course, it's during mounting works. On the next slide, you will see how it looks like on operating nuclear power plant. So during mounting, you see this turbine naked, without covers. And turbine, of course, it's a complicated structure. It's not usual some rotating wheels, because this turbine consists of several stages of cylinders of high pressure, low pressure, connected in special manner. And actually, you see on this picture, all these elements, it's one turbine, several different cylinders connected between. So one kind of equipment. Very important item is turbine condenser. For Russian design VVER nuclear power plant, every turbine has several condensers, at least two, from both sides. So turbine condenser, you see scale, very big equipment, and it looks like modular construction, because and inside actually all this structure you see, I don't know, like butterfly maybe. It's actually it's holes of tubes, because condenser it's actually like very big, not cube, but you see very big construction with a lot of tubes inside. In this kind, it's some similar to steam generator, but in condenser idea is to provide outside water, for example, from cooling tower or from pond or from river, in these tubes, just to cool down steam inside of this condenser. So condenser is very important too for nuclear power plant, and you see this equipment as well. During operation, of course, after mounting, this condenser will be welded inside of all other systems. The next element of secondary circuit, the aerator. The aerator, one of the biggest. You see on this picture, with the aerator before mounting, after transportation on nuclear power plant, you see very big one equipment, and this equipment is equipment of secondary circuit is intended to actually aerate, just to remove all gases dissolved inside of water of secondary circuit. So it looks like small submarine you see on this picture. And turbine hall on operating nuclear power plant. This photo from Tianwan nuclear power plant with VVER 1000. For VVER 1200, actually it looks similar. So this is operating nuclear power plant. So you see all turbine cylinders actually is closed under special covers. And you see some pipelines with steam and actually steam distributing pipelines nearby this turbine. And for example, this part, it's bearing. It's a bearing of shaft of turbine. And I guess from our side, where is generator connected to turbine. And for example, this big equipment in the front of this photo, it's actually separator of turbine, because between stages of turbine there is separation and reheating of steam, just to improve thermal efficiency. And all this equipment, secondary circuit, of course, all layout, all structure of secondary circuit is designed to provide highest possible thermal efficiency. Because I hope you know, every industry installation facility to produce electricity, to provide heat and so on, can be characterized by thermal efficiency, measured from 0 up to 100%. And of course, our wish, of course, to provide highest possible value. For nuclear power plant, unfortunately, this thermal efficiency not so high like for thermal power plant. For thermal power plant, for gas power plant, nowadays this thermal efficiency can be up to 70, I don't know, 75% maybe. For nuclear power plant, VVER and PWR as well, nowadays this thermal efficiency is about approximately 37, 38 maybe. Because using usual water cycle, it's actually very hard to make this value bigger. But for other types of reactor, it's possible to provide close to 50%. And like example, only for our reasons, on this slide you see some simplified diagram of between temperature versus specific entropy. And as usual, these diagrams are used to calculate thermal efficiency of the cycle. And of course, just to develop, just to construct a secondary circuit and for future to provide operation, we should to use courses of engineering thermodynamics, special course in this area. Of course, it's very important, first of all, for personal for turbine shop and for reactor shop as well. By the way, reactor and turbine shops are very connected, because from one side, yes, primary circuit and reactor, it's one part, nuclear part, and secondary circuit can be considered like common part. But actually, both parts during operation is closely connected, and some changing, some noises in one part can be linked with primary circuit and vice versa. So of course, this course is very important for both reactor shop and turbine shops. When I said about electric shop and instrumentation shop, of course, it's not nuclear in idea, because electric shop actually it's usually like electrical engineering, just to provide operation of all electrical equipment, huge number, starting from usual bulbs, electrical bulb, and finally up to generators. Personnel of this shop should maintain all this equipment in good condition. And when we say about instrumentation shop, this personnel is responsible for all instrumentation, all gauges, all devices, measuring different parameters. And by the way, number of personnel in these shops are very, very multiple, several up to 100 personnel in every shop. So, like example, on this slide, you see photo of upper part of reactor unit with all cables from sensors inside of core, because during operation there are a lot of neutron measurement channels inside of reactor and thermocouples to measure temperatures. And of course, all this equipment connected with cables, because on nuclear power plant nowadays it's all connections, as usual, it's through wires. There are no wireless connection in different reasons. So, of course, it's just to estimate scope of works for this personnel. And of course, personnel from these shops should have knowledge in electrical engineering and electronics, as usual. Around operation of nuclear power plant, there are a lot of different areas, not only operation, but as I said, for example, inspection and diagnostics of nuclear power plants. Yes, it's like some additional area, but it's very important for operation too, and it's different kind of non-destructive testing, like ultrasonic, like radiographic X-ray examination, like eddy current, and so on. And for example, on these slides, you see photos from our summer school we provided in our university in non-destructive testing for foreign students. Moreover, some students from Bangladesh master program in our university gone through these courses, summer school. And in this year, this summer school will be was realized in online format due to coronavirus. But in general, we realized this summer school as usual in usual manner during 1 week in Russia. The next area, very important, and I guess it's obvious for all, it's dosimetry and radiation protection. As well, it's like service area of operation. But of course, anyone knows about nuclear power plant. It's potentially hazardous object, and of course, this object with radiation in some areas. Radiation means, first of all, of course, reactor vessel and equipment of primary circuit. And the task of personnel from radiation protection department, first of all, to organize all work, all procedures on nuclear power plant in such a way to minimize this exposure for personnel. And of course, very special devices. Of course, this area, first of all, is based on nuclear physics, first of all. And we provide special courses in dosimetry during education. And for students, for foreign students as well, we provide summer school in radiation monitoring to provide some knowledge, not only how to measure effect of ionizing radiation, but for example, how to make measurements of for environment. Because maybe you know, around of your nuclear power plant, Rooppur, will be installed a lot of special devices to measure the radioactivity inside of buildings, outside, in the site of nuclear power plant, and moreover, I guess in different points in nearby villages, towns, should be some points of measure of radiation background, just to be sure all is okay. So during this summer school, students can get knowledge in this area as well. And of course, now I've just considered maybe main parts and main areas of knowledge when we say about nuclear engineering, especially about nuclear power plant. But of course, there are more courses. Of course, it doesn't mean this course is not so important. It's important too, but for some specific departments. First of all, we should say about material science. Material science, of course, is very important, but first of all, material science is very important for developers. For developers and for specialists in manufacturing of different elements, first of all, fuel and elements of primary circuit. Because material science is very important, because during operation, fuel and construction materials like steel, like zirconium, will go through changing of form, changing of geometry, and different effects like swelling. So we should to know about these effects, and we should to minimize effect from different irradiation for operation. So we need to know about material science. Of course, material strength. First of all, if we say about personnel of repair shop and so on, and fracture mechanics. Fracture mechanics is important for repair and for diagnostics and non-destructive testing. So, of course, there are a lot of different courses, more specific for more narrow areas of operation of nuclear power plant. But you see, there is no so nuclear specific. And maybe main question in my presentation, I think it's better to put this question closer to end of this presentation. But why? Why nuclear power plant personnel should know physics? Because when we say about developers, engineers who will develop, design, and manufacture equipment, of course, it's obvious. All this personnel should have knowledge in some specific areas just to provide calculations and so on. But when we say about nuclear power plant, it's a good question because, for example, for Bangladesh, Russian Federation and Rosatom company, like as vendor of reactor technology, yes, will provide this enterprise actually at turnkey stage. So you will get fully completed nuclear power plant just to operate. But of course, all personnel should, not all, but nuclear power plant has a lot of people in personnel. For 2 power units nuclear power plant, it should be more than 1,000 people anyway. But of course, not all these people nuclear engineers, of course. As usual, there are some part of personnel strictly nuclear, several hundred men's or women's of personnel, and a lot of people just to provide service functions like maintenance, repair, and so on. But anyway, when we say about nuclear personnel, like operators of turbine, of reactor, and so on, yes, there is huge automatic system, automatic control regulation system, and many operations, many procedures during operation of nuclear power plant will be realized in fully automatical mode. But anyway, the key personnel, key operators, of course, should have deep knowledge of physics, because in this way, this personnel will get more deep understanding of all processes during normal operation. First of all, processes means nuclear processes, thermohydraulic processes. First of all, the main processes for operation of nuclear power plant. And during normal operation, it's okay, but of course, especially this knowledge is very important in case of violations of normal operation. Violations, it means not some accident. No, it means nuclear power plant, it's huge organism, huge enterprise with a lot of different elements, equipment, and so on. And of course, there are possible situations with unpredictable and maybe undesirable behavior of some elements. And of course, especially in these situations, role of operator, human operator, is very high, because it looks like autopilot for planes. Because for aircraft, for usual flights, usual planes, we have pilots, and role of these pilots especially important for initial stage of flight and during landing, for takeoff and landing, the most important stages. For nuclear power plant, it looks like this one. The most important is time of startup of power unit from 0% of power output up to 100, and then shutdown, safe shutdown from 100 up to 0 actually. And during base mode, during stable operation, of course, it's not so interesting from point of view operator. It's unstable producing of electricity. So many years practice say about it's very important for operators know physics just to provide right behavior in case of violations of normal operation. Of course, next point, this knowledge of physics important for diagnostics of equipment and interpretation of operational data. It may be similar to medicine. In medicine, special doctors should to have huge knowledge in chemistry, in biology, in different life science to provide right diagnosis. Actually, the same for nuclear power plant. When you have some data, operational data about flow rates, about temperatures in different points of circuit, and you like to want to know what is mean. Is it right? Is it wrong? Maybe it's some malfunction for some equipment. It looks like diagnosis, but not for human, but for equipment. And of course, in this case, this knowledge of physics is very important. And important point I'd like to mention, it's very important to be acquainted with nuclear specific for all personnel, not only for operators, for every electrical engineer, for every repair personnel. Of course, there is no need to have deep knowledge in nuclear physics, not. But for example, some guy will just repair pipeline, maybe to welder, maybe with some mechanic, just to cut pipelines in two parts and so on. But anyway, all personnel on nuclear power plant should go through special instructions, because nuclear power plant, it's not usual thermal power plant, very nuclear specific. And of course, all personnel should have some basic knowledge about this nuclear specific, because on Russian nuclear power plants, on Western nuclear power plants, there were many situations of some accidents, first of all, due to human factor. Because, for example, some repair personnel just closed some valve. But this valve was very important for some process, and this event could be very important for future consequences, for example. So, in this reason, short instructions, short course, just about what is nuclear power plant is, it's very important for all people connected with operation of nuclear power plant. And of course, knowledge of physics is very important for safety culture. Maybe you know safety culture, it's not technical, it's more psychology and sociological event, because after accidents, it's important from IAEA agency for all personnel of nuclear power plant to cultivate this safety culture. Everyone on nuclear power plant during every operation should keep in his mind or her mind about possible consequences, about possible influence on equipment and so on. So safety culture, it's about think about safety anyway. Every minute on nuclear power plant, you should to think about safety of all nuclear power plant totally, and you should to think about consequences of all your events, all your actions on nuclear power plants. And physics, like as science, of course, is very important, and because physics actually it's base for all future courses for nuclear power plant specific. And finalizing my presentation, I'd like to briefly say about, on previous slides, you saw some installations and facilities used to train students in our university. And when we try to provide upper level of knowledge in nuclear power plant operation and so on, of course, we use special equipment just to collect all knowledge together. First of all, we say about analytical simulators of nuclear power plant. It looks like a special room with working places, and every working place you see has several monitors with screens of like these ones. You can see, I don't know, distribution of heat inside of reactor. You can see on the layout, on diagram, you can see cross cross connection of different variables, pressures, flow rates, and so on. You can model different situations on nuclear power plant and so on. Of course, it's special computer codes. Special computer codes to model, to simulate behavior of nuclear power plant, but of course in computer, because it's very important to train future engineer, future specialists for nuclear power plant. Then we have special practical training. Practical training, as I said, we have resource centers. We have Obninsk Center, and we have two more in Novоворonish and Volgodonsk. It's cities inside Russia, in Russian Federation. In Novоворonish, there is first in the world VVER 1200 megawatts power plant. And in Volgodonsk, there is nuclear power plant VVER 1000, but as well there is Atomash manufacturing plant, whereas all huge equipment like reactor vessels, steam generators, pressurizers, all this equipment can be manufactured at this facility. So we have special training for our students. You see photos in this manufacturing plant. You see students on control room of real nuclear power plant and on simulator, because this is analytical simulator, like usual room inside of university just to provide special practice. But on a real nuclear power plant, there is a full-scale simulator, separate building, where all actions can be trained beforehand, before operation of nuclear power plant. And moreover, in Rooppur nuclear power plant, the same full-scale simulator training center will be constructed before startup of nuclear power plant itself. And about safety, very briefly. About safety, of course, safety is around all actions during operating nuclear power plants. First of all, we have protective barriers on nuclear power plant. And for VVER, there are 4 barriers: fuel matrix, cladding of fuel rod, primary circuit, and containment. And actually, we say about what is prevent to release of radioactivity, possible release of radioactivity. So all these actually barriers, structure of this fuel, as I said, hermetically sealed fuel rod with thin walls, primary circuit, all this equipment of primary circuit is sealed again, and containment, building itself with all mine equipment inside. And I'd like to mention passive safety systems. It's specific of VVER 1200 and your nuclear power plant in Rooppur as well. And passive systems, it's about systems to realize different safety functions, but without any power supply outside. Because, for example, when we say about many systems, some systems is active ones. It's a good system, good systems, very effective, but you should to have outside power supply to work, to operate these systems. But maybe you know, after Fukushima accident in Japan, it was proved that a lot of systems should be provided to work without any power supply during at least, I don't know, several hours. So in VVER 1200, there are a lot of special safety systems, and a connection with physics when we say about safety. Many of these systems, as I said, there are no supply. For example, whereas you see this one, heat exchanger of passive residual heat removal system. And by the way, this system should work without any power supply, without any compressors, without any pumps, and flow of cooling air through this system actually is provided by natural law without any special equipment. But to calculate and to get knowledge about work of these systems, of course, knowledge of physics is very important. And one more example of safety equipment, maybe it's special molten core catcher. It's a unique feature of VVER 1200. Special equipment located beneath of reactor vessel. Beneath of reactor vessel itself, and idea and goal, final goal of this equipment catcher is very simple. In case very small probability, but in case of melting of core, this catcher actually should to collect all corium, all melting fuel with steel and so on, and to distribute in such a way to minimize exposure, radioactive exposure, and actually to provide cooling and finally freezing of all this corium. So it's special equipment, and it's very interesting idea, physical and chemical, how to provide this distribution of very hot mass of fuel, and how to realize cooling of this corium and finally stabilizing. So it's one example of a very interesting element of safety system. So I think it's enough for our very short presentation. Thank you very much for your attention, and I'm ready to answer to your questions. Dr. Pretam?
So thank you, sir.
Yeah.
So for your wonderful session. So I think students have enjoyed lots and learned a lot of things from your session, because here you have shown some practical picture of our reactor. So if you allow us, then we can start our discussion.
Yeah, yeah.
So we
Sure.
have already got with us Sheikh Ahmed Sakib Bhai from he's a development manager from Information Center on Nuclear Energy of the Future. So welcome Sakib Bhai to our webinar.
First of
Thank you
all,
very much.
yeah, I'm glad to see you again.
Yeah, I'm glad to see you too. How are you, Mr. Nakhabov?
Thanks. Great.
It was very great to hear you speak. Last time I enjoyed it. Today I enjoyed it a lot. Thank you very much. And thank you very much to Dr. Pretam sir for letting Energy of the Future be a part of this wonderful initiative of yours. This series of webinars that you have been organizing for the past couple of months, these are very helpful for the students, especially the students who are studying physics or nuclear engineering. I think they have learned a lot today, and I'm so glad that we could participate in this particular session.
Thank you for so successful this session, for helping us.
I think so. And also, I'd like to thank Mr. Alexander Nakhabov very, very much to manage some time to speak in front of us. He's a very well-renowned professor in nuclear physics, and according to his students in Russia, I have some friends there, they say that he's a very student-friendly professor, as we have all seen, and his lectures are very awesome, as we have all seen today.
Thank you very much.
Yeah. I personally have had the experience to hear him speak when he was here in Bangladesh last February to participate in the Olympiad Precise Energy that Energy of the Future organized. I've seen that he has a way of explaining the most complicated things about nuclear studies very simply, yet in an elegant manner. I think Dr. Pretam sir, you agree with me on this point?
Yeah, of course.
And I hope the students who have watched this session have enjoyed his lecture as much as I have. And I think we I hope that we can participate in the future events like this when you organize.
Okay,
thank you very much, everyone.
Yeah, thank you for helping us. So we have some question in Facebook. They have actually commented. So if you allow, then I can read it out.
Yeah.
So first question. So please inform us the fundamental or basic difference between the traditional PWR, usually US PWR or a VVER, and the future evolution of VVER.
So question is about future evolution.
Future evolution and the basic difference between PWR and VVER.
Okay, so yes, first of all, about PWR and VVR. Actually, VVR can be considered like a Russian version, maybe PWR technology, because I hope you know PWR is the most prominent reactor technology in the world. Majority of reactors all around the world of this type. And actually, there are several not important difference, but visible difference. First of all, in PWR, there is form of fuel. For PWR, form of fuel is square, cross-section of fuel assembly. For VVR, as you saw, it's hexagonal form. It's just, of course, all difference, it's tradition. Because Western PWR from United States, from France, first of all, and VVR, both technologies have more than 50 years of operation experience. And actually, it's like tradition. But as I know from point of view of reactor physics, yes, there is difference between, because we, in for square fuel and for hexagonal fuel, we can realize different diameter of core, the same power output, for example. So different form of fuel, different type of steam generators. For PWR nowadays, of course, as I know, as usual, it's a vertical type. It's huge steam generators, as I know, 20 meters in height, maybe 2 steam generators. For big power unit, maybe more. But in Russian design, as usual, we use horizontal type. As I discussed this point with specialists in thermohydraulics, both construction have some advantages, disadvantages, as usual, you know. But maybe in future, maybe for VVR, vertical type can be considered. Because as I know, for greater power output, maybe vertical type has some advantages. But actually, PWR and VVR, it's actually only 2 different kinds of one technology, with no so strict difference between. If we say about future, about evolution, it's a very good question, actually. Thank you very much. Because, you know, from one side, VVR 1200, it's up to, it's advanced and actually newest type of this reactor, because VVR 1200 is the first in the world reactor of generation 3+, and first reactor of this type was put into operation in Voronezh in Russia in 2016. So now actually it's only 4 years of operation experience for especially this type of reactor. And the second type is Westinghouse AP 1200, I guess. It was put into operation in China last year. So, but future evolution of VVR, actually, as I know, it's hard. It's hard to provide evolution because it's not only for VVR, I guess for PWR the same. Because it's nowadays, this construction is very advanced. As I know, it's very hard to improve values of thermal efficiency and main parameters. Because, you know, for 60 years, our specialists, our engineers, American engineers, France engineers, I guess these guys made the best to provide this construction. And it's very hard to improve. As I know, in future, in Russian Federation, first of all, if we say about this kind of reactor, we say about so-called supercritical reactors, when we use not pressurized water, but use water of supercritical parameters of not 16 megapascals, I don't know, but more than 100 megapascals maybe. And as I know, it will be actually not usual water. It's some new kind of, from point of view of physics, it's new kind of water actually. And supercritical installations. And maybe, you know, when we say about future, it's better to say not about VVR, but about future of nuclear engineering in our countries. And first of all, we say about generation 4. Generation 4 of reactors its IIA area. And moreover, we will say about fast Newton reactors, because VVER is good enough, and moreover, Rooppur nuclear power plant is designed for 60 years of operation life with ability of prolongation. So actually, when we say about Rooppur nuclear power plant, we say about 100 years of operation up to final shutdown. So if we say about future 50 years, 60, 100, actually VVER and PWR, I think, can safely work during this time. But for future, of course, first of all, we should think about fast neutron reactors and more sophisticated, but not water. Because Dr. Pretam from physics department, of course, knows about, when we say about cycles, thermodynamical cycles, of course, for water, we have some threshold, actually. Of course, it's much more interesting to use liquid metals, for example. In this case, we can get much more efficient installations. So about evolution, I think supercritical and these kinds of installations.
Okay, thank you, sir, for your answer. So we can go our next question. So actually, the next question is, sir, I want to know about the importance of emergency cooling system, ECCS, and how it will work.
So how emergency cooling system works? Yes.
Yeah.
Okay.
And importance of it.
I think right now, do you see my presentation or not?
I don't know. Maybe he may present your lecture.
Yes, maybe. So for me, because
we can add.
And do you see something right now?
Yeah, we can see.
Okay. So maybe I will not maximize full screen, leave in this.
Here.
Yeah, I'd like to comment this question using layout. Yes. So yes, this emergency core cooling system, actually, it's simple. It's simple. Not simplest, but simple system, because there are several systems of safety. And idea is very simple one. In every situation, one of our concerns about future of reactor fuel, first of all, is cooling. In every accident, we should to provide adequate cooling of nuclear fuel. For example, first of all, in case of leakage. First of all, maybe you know, there is so-called LOCA, loss of coolant accident, and of course, for example, breakage of some pipeline. In this case, our water from primary circuit will go out in containment, and of course, level of water inside of reactor will decrease. And of course, it's very dangerous for fuel. And first of all, we want to provide adequate volume of water inside of reactor. And the first primary target of this emergency core cooling system in this one. We have several hydroaccumulators, very big tanks. As I know, one hydroaccumulator volume approximately maybe 60 cubic meters. And actually, this is water of primary circuit, not usual water, but water with boric acid dissolved, because in VVER we have control rods to control chain reaction, and we use so-called boron regulation. We have boron accident dissolved in primary circuit water, and boric acid because boric acid is a very good absorber of neutrons. So we have specially treated water, and it's very interesting idea of working principle of this tank. You see, yes, a hydroaccumulator and pipeline between hydroaccumulator and primary circuit. And of course, there is some valve on this pipeline. And this valve is fully automatical. After decrease of pressure beneath a wall, beneath of some threshold, in this case, this wall will open automatically, and all water from steam, not from head accumulator, just go inside of reactor vessel, and in this way we can provide for some short time, we can provide huge volume of water in the primary circuit. And moreover, for modern VVER, on this picture, you see, actually on this picture, actually for next stage of VVER. Next stage is VVER toy, so-called, and this power unit not for export now. First VVER toy now under construction in Russia. For VVER toy, it will be three stages of hydroaccumulators. For VVER 100 to 1000, where there are two stages. First one and second one, for different thresholds of pressure. And actually, this system, it's system for first time. Just after possible accident, the system designed to provide a lot of water inside of reactor. If we need to provide cooling after this time, we should to use other systems for these reasons. So with some answer for this question.
Thank you, sir. So we have another question. Maybe this is the last question. So is it safe to build NPP in a populated residential area like Ishodi or other place? What's your opinion?
Maybe I can't get idea of this question. Yes.
Okay.
Could you explain, please?
So actually, he want to know that is it safe to build a NPP in populated or dense populated area?
Do you mean dense area? You mean population around? Yes.
Population.
Yes, I know these concerns from Bangladesh part, first of all, because Bangladesh is very dense populated country, as I know. And moreover, in Bangladesh, there are the same population in the Russian Federation nowadays, maybe greater. Yes. And first of all, of course, you know, it's not a Russian vision. It's actually there are regulations from IAEA agency, international agency, and there are some not restrictions, but actually rules. Because when site for nuclear power plant should be chosen, of course, first of all, we say about different physical properties like seismic, like possible tsunami, and so on. And of course, we say about population. It's in basic words, yes, it's not dangerous because anyway, after I guess in Rooppur it will be the same. There is nuclear power plant, perimeter of nuclear power plant, and there is some area around nuclear power plant not for living. I don't know, maybe several kilometers away. But actually, during operation and during construction, a nuclear power plant will be equipped of special systems, safety systems and so on, and monitoring systems. When I said about dosimetry, as I know, around of nuclear power plant, it will be a lot of special sensors to measure radioactivity in all situations. Because VVER 1200 nuclear power plant is designed in such a way just to eliminate need of evacuation of people. In every situation, in case of every accident on nuclear power plant, possible region, I don't know, of influence of this accident should be restricted only by site of this nuclear power plant. So no release of radioactivity or some hazardous agents outside should be prohibited. So in this way, of course, it's not dangerous, and moreover, I think it will be attractive because you know it's huge enterprise with a big number of possible positions for works, not on nuclear power plant itself, but around of nuclear power plant, just in logistics, in transport, and so on and so on. So it's very big very big enterprise. And in this sense, now I'd like to provide some parallel with hydro. All people, I think, know about hydro power plants, yes, on rivers or oceans. And of course, the same question: is it dangerous to live around hydro? Because yes, we see very powerful dam, and it's great, but we should keep in our mind that very small probability of breakage. And in this case, of course, it will be very dangerous. But in usual situation, if all construction and mounting well done, of course, it's only very big, very interesting industry enterprise.
Thank you, sir. I think in our VVER we have a very good safety feature, so we don't think don't need to panic about that. So we have one more question, maybe one or two questions. One of our students asked to know about the criticality of a reactor in brief.
Once again, critically, or what do you say?
Can you please tell about the criticality of a reactor? Critical point, maybe. Or another question: is it possible to construct a mini reactor instead of mechanical engine, which can be used to car, bus, etc.? Maybe we have in submarine a small reactor.
But if I understand right, this question about critical reactor, it's about another type of reactor, yes?
Criticality, maybe.
Criticality is just stage. Criticality, you know, it's actually its main operating stage of reactor when for every neutron absorbed in uranium, you will get one neutron. It's actually usual situation for operation of nuclear reactor, because from point of nuclear physics, actually only three possible situations. One situation when you have more absorbed neutrons than new ones. In this case, your chain reaction will be suppressed only. The criticality stage, when you have stable producement of neutrons. And you have a situation criticality, upper critical situation. In this case, like in nuclear bomb, actually, when for one neutron absorbed, you will get three, for example, neutrons burned in a fission reaction. For nuclear reactor like VVER and PWR, usual reactors, of course, criticality is main mode, because using our control system, anytime we provide this balance of absorbed neutrons in uranium and new neutrons after fission reaction. Only in this situation we can provide this stable producing of electricity. But by the way, when changing power level, for example, you want to go through, I don't know, 50% up to 75% of power output. In this case, yes, you should to, for some short time, you should to provide upper criticality mode, because you should to increase power output. And then you should to stabilize the situation. Of course, all these manipulations, of course, should be provided in special safety manner. And of course, especially in this reason, there are a lot of special sensors to measure neutron flux, to measure temperature, just to provide this safe possibility. Because yes, nuclear reactors, it's special device to provide this critical situation.
Okay, thank you, sir. So maybe this may be the final question. Is it possible to construct mini reactor instead of mechanical engine, which can be used to car, bus, etc.? Is it possible?
Which kind of reactor is it possible to?
Mini type reactor, which can be used in bus, car, to replace the mechanical engine. Is it possible? One student actually asked about this.
Actually, maybe I don't get maybe idea as well.
Yes, very difficult.
Yes, okay. Because there are different types of reactors. So Maybe you reformulate this question.
Okay, I think we should conclude our discussion session. Thank you for wonderful session, and thanks to Sakib Bhai for helping us to arranging this session. And hopefully we will get you another session for our student in near future. And I think we have something left. So if you give us some time in the near future, then I think student may be benefited. So thanks a lot, and I'd like to say thanks again on the behalf of Pabna University of Science and Technology. And maybe Sakib Bhai can say something.
Yeah.
It's okay. I don't have anything to say anymore. It was our honor again to participate in this particular session. And again, Mr. Nakhabov, it was a very good session. I think the students have learned a lot. I think we should do any more of these sessions in future.
Hopefully see you.
Thank you very much.
Yeah, thank you. Thanks a lot.
Very much for you.
Good night. And maybe in your in Russia it's not night, but for our part it's night.
It's not night. It's evening. Yes.
Yeah. So goodbye for today.
Yeah. Thank you very much. It was my pleasure. Yeah. And I hope to see you again.
Yeah, of course.
Via internet or maybe personally in future. Thank you very much.